The relationship between the inside and the concept of quantum complexity adds temporal depth. The inside grows because the quantum complexity of the state increases. The complexity growth is linear for an exponentially long time. The inside deepens, stretches, generates new space. The singularity is the point where complexity exceeds geometric capacity. What physics tells us about the inside is that it is dynamic, not static, growing and evolving even after the exterior has reached thermal equilibrium. The connection between the inside and the concept of the Planck star connects the quantum resolution to specific physical properties. The Planck star has the Planck density, roughly 5.1 times 10 to the power of 96 kilograms per cubic meter. It has a radius of roughly the Planck length. It preserves information. It eventually transitions to a white hole. What physics tells us about the inside includes this specific physical picture, a tiny, hyperdense, information-preserving core at the center. But here is what makes this truly terrifying. We cannot check. The event horizon prevents any signal from escaping. Everything physics tells us about the inside is theoretical. The most important predictions in all of physics cannot be directly verified. The inside of a black hole is the most important place we can never observe. The question of what physics tells us about the inside of a black hole has generated a landscape of proposals, each using different theoretical tools, each revealing a different aspect of the interior. What follows is a survey of what each major approach to quantum gravity says about the inside. The first approach is the classical general relativistic interior. According to general relativity alone, the inside of a non-rotating Schwarzschild black hole is a smooth, contracting spacetime that terminates at a singularity. The falling observer crosses the horizon, experiences the inversion of space and time, falls through a contracting geometry, and is destroyed at the singularity. This is the textbook answer. It is mathematically precise, and most physicists believe it is incomplete. For a rotating Kerr black hole, found by Roy Kerr in 1963, the interior is more elaborate. The Kerr solution has two horizons, an outer event horizon and an inner Cauchy horizon. Between them, space and time are inverted. Beyond the inner horizon, they revert. The singularity is a ring rather than a point. The mathematics formally permits paths through the ring into entirely different spacetimes. But the inner Cauchy horizon is almost certainly unstable. The mass inflation instability, demonstrated by Werner Israel and Eric Poisson, shows that infalling radiation is blue-shifted to arbitrarily high energies at the Cauchy horizon. The curvature diverges. The inner horizon is replaced by a singularity. The elegant Kerr interior is a mathematical idealization that does not survive contact with reality. What physics tells us about the inside of a real rotating black hole is that it is messier, more violent, and less understood than the textbook picture. The second approach is string theory. String theory replaces point particles with one-dimensional vibrating strings, roughly the Planck length in size. The finite size of the string prevents the compression to zero volume that produces the singularity. What physics tells us, through string theory, is that the singularity is replaced by stringy physics, a complicated regime where the classical geometric description gives way to the full string theoretic dynamics. The string theoretic approach to the inside has produced one of the most important results in theoretical physics, the microscopic accounting of the Bekenstein-Hawking entropy. Andrew Strominger and Kumran Vafa showed in 1996 that for a specific class of extremal black holes, the number of string-theoretic microstates matches the macroscopic entropy formula exactly. This demonstrated that the inside has genuine microscopic quantum states that can be counted explicitly. The inside is not an empty void. It has structure, complexity, and countable degrees of freedom. The fuzzball program, developed by Samir Mathur, provides the most explicit string-theoretic picture of the inside. The entire classical interior is replaced by a tangled web of strings and brains. There is no event horizon in the traditional sense. There is no singularity. The black hole is a fuzzball, a ball of stringy material. Each fuzzball configuration is a different microstate. For a solar mass black hole, the number of microstates is 10 to the power of 77, matching the Bekenstein-Hawking entropy. The numbers are striking. The fuzzball provides a microscopic accounting of the black hole entropy. one of the most important achievements of string theory. What physics tells us, through the fuzzball program, is that the inside may not be the smooth, empty, classical spacetime that general relativity describes. It may be filled with quantum gravitational structure from the would-be horizon all the way to the center. The third approach is loop quantum gravity. Space-time is discrete at the Planck scale. The singularity is replaced by a quantum bounce. When matter collapses to the Planck density, the discrete quantum geometry generates a repulsive pressure that halts the collapse. The density reaches a maximum, roughly 5.1 times 10 to the power of 96 kilograms per cubic meter, and the matter bounces. What physics tells us, through loop quantum gravity, is that the inside of a black hole is not a dead end. It is a passage. The matter collapses, bounces, and expands. The black hole connects to a white hole through a quantum bridge at the Planck scale core. The Planck star, proposed by Carlo Rovelli and Francesca Vidotto, provides a concrete picture, a compact object at the Planck density, the smallest and densest possible configuration, finite and well-defined. The work of Hal Haggard and Carlo Rovelli explored the transition from black hole to white hole. The transition time, as measured by an external observer, may be very long, but the falling observer would experience the bounce in a very short proper time. What physics tells us is that the inside of a black hole may be temporary, a transit lounge between collapse and expansion. The connection between the inside and the Wheeler-DeWitt equation provides the deepest conceptual perspective. The equation has no time variable. The quantum state is static. Time must be reconstructed from internal correlations. The inside, where classical time ends at the singularity, is where the emergence of time fails. The fundamental timeless quantum state persists. The temporal output ceases. The Bekenstein bound sets the maximum information content of the inside. Black holes saturate this bound. The inside is the densest information store in nature. The Margulis-Levitin theorem sets the maximum processing speed. The inside operates at this limit. What physics tells us about the inside is that it is the most extreme quantum information system in the universe. The concept of the Penrose-Hawking singularity theorems guarantees the classical singularity, but not the quantum one. The theorems require positive energy density, which quantum effects can violate. They require trapped surfaces, which quantum corrections can modify. The classical guarantee evaporates when the framework changes. What physics tells us about the inside depends on which physics we trust. The thermodynamic constraints from the four laws, the Hawking temperature, and the Bekenstein-Hawking entropy form a tight web. Any description of the inside must satisfy all of them simultaneously. The constraints are independent and complementary. Together they narrow the space of possible descriptions dramatically. The fourth approach is the holographic principle and AD-SCFT. Juan Maldaceno's 1997 discovery showed that a theory of gravity in anti-de Sitter space is exactly equivalent to a quantum field theory on the boundary. The boundary theory has no singularity, no event horizon, no classical interior. It is well-defined, unitary, and singularity-free. What physics tells us, through holographic duality, is that the three-dimensional inside of a black hole may not be independently real. It may be a holographic projection, a three-dimensional image generated by two-dimensional boundary physics. The classical interior, with its singularity, is a feature of the projection, not of the underlying reality. The boundary theory provides the fundamental description. The bulk interior is derived. The island formula, developed in 2019 and 2020, provides the most recent insight. It showed that the entropy of Hawking radiation follows the Page curve, confirming that information is preserved during evaporation. The calculation includes quantum extremal islands, regions of the interior that are informationally connected to the radiation rather than to the black hole. What physics tells us, through the island formula, is that the inside is not as sharply separated from the outside as the classical picture suggests. Parts of the inside belong, informationally, to the outside. The causal set theory approach, developed by Raphael Sorkin and others, proposes that spacetime is fundamentally discrete, composed of individual events connected by causal relations. In a discrete spacetime, a point-like singularity cannot form. The inside reaches a maximum density determined by the fundamental spacing. What physics tells us, through causal set theory, is that the inside has a granularity, a minimum scale, that prevents infinite density. Asymptotically safe gravity, initiated by Steven Weinberg in 1979, proposes that the gravitational coupling approaches a finite fixed point at high energies. The curvatures near the singularity are bounded. What physics tells us, through asymptotic safety, is that the inside reaches extreme but finite curvatures, never producing the classical infinity. The concept of the Penrose-Hawking singularity theorems must be placed in proper context. The theorems guarantee singularities within classical general relativity. They do not apply to quantum gravity. The theorems require positive energy density, which quantum effects can violate at the Planck scale. The classical guarantee evaporates when the mathematical framework changes. What physics tells us about the inside depends crucially on which mathematical framework we use. The fifth approach involves quantum error correction and emergent spacetime. The holographic encoding of spacetime has the structure of a quantum error correcting code. The inside is encoded in the boundary through a redundant, error-resistant mapping. Near the singularity, the code degrades. At the singularity, it has broken down. What physics tells us is that the singularity is a failure of the code, not a failure of reality. The information survives on the boundary. The geometric description of the inside has lost coherence. The holographic perspective transforms the question of what the inside is. In AD-CFT, the boundary theory has no event horizon, no singularity, no classical interior. The inside is a derived quantity, a geometric projection of boundary quantum physics. The boundary theory is the fundamental description. The inside is secondary. The error-correcting structure of holographic spacetime provides the mechanism. The inside is encoded in the boundary through a quantum error-correcting code. Away from the singularity, the code is robust and the inside is well-defined. Near the singularity, the code degrades. At the singularity, it fails. The inside ceases to have a well-defined geometric description, but the boundary information survives. The Ryu-Takayanagi formula connects the entanglement entropy of boundary regions to the areas of bulk minimal surfaces. The quantum version leads to the island formula. These formulas establish the mathematical connection between quantum information on the boundary and geometry in the inside. The inside is generated by entanglement. It is sustained by error correction. It breaks when the code fails. The convergence of independent approaches is the most important thing physics tells us about the resolution of the inside. String theory, loop quantum gravity, holographic duality, causal set theory, asymptotic safety, the gravitational path integral with replica wormholes, all agree that the classical singularity does not exist. All identify the Planck scale as the resolution point. All preserve information. All suggest spacetime is emergent. This convergence is powerful evidence, even in the absence of direct experimental verification. When independent theoretical frameworks, starting from different assumptions, arrive at the same conclusion, the probability that the conclusion is wrong is small. What physics tells us about the inside is increasingly well constrained by this convergence. The thermodynamic constraints reinforce the convergence. The Bekenstein-Hawking entropy, the Hawking temperature, the four laws, all must be reproduced. The constraints are independent of and complementary to the quantum gravity constraints. Together they form a tight web that narrows the space of possible descriptions dramatically. The relationship between all the proposals and the Planck scale deserves emphasis. Every approach identifies the Planck density as the resolution point. Every approach replaces infinite density with the Planck density. Every approach preserves information. Every approach suggests spacetime is emergent. The Planck scale is the mathematical and physical frontier where the classical description gives way to the quantum. The gap between the Planck scale and our experimental capabilities is vast. 17 orders of magnitude separate the distances probed by the Large Hadron Collider from the Planck length. No foreseeable technology can bridge this gap directly. What physics tells us about the inside at the Planck scale must come from theory, from mathematical consistency, from the constraints of the information paradox and black hole thermodynamics. The gravitational path integral provides powerful evidence. Summing over all geometries, including replica wormholes, produces finite unitary answers. The singularity is washed out. The quantum theory of the inside is singularity-free. Individual classical geometries contain singularities. The quantum sum does not. The Penrose-Hawking theorems guarantee singularities within classical general relativity. But the theorems require positive energy density and trapped surfaces. Quantum effects at the Planck scale can violate these conditions. The classical guarantee evaporates in the quantum theory. What physics tells us about the inside at the quantum level is that the classical catastrophe is avoided. The observational constraints from gravitational wave astronomy are tightening. Each merger detection tests general relativity in the strong field regime. Future detectors will push further. The Event Horizon Telescope may resolve the photon ring. Each observation constrains the inside by testing the exterior with increasing precision. The connection between the inside and the concept of the multiverse is speculative. The Kerr mathematics permits paths through the ring singularity into other spacetimes. If the quantum gravitational resolution preserves this feature, the inside might connect our universe to others. This remains far from established physics. The gravitational path integral, summing over all spacetime geometries including replica wormholes, produces finite unitary answers. The singularity is washed out in the quantum sum. The inside in the full quantum theory is singularity-free. Individual classical geometries contain singularities. The quantum sum does not. The computational complexity perspective adds temporal dynamics. The inside grows because complexity increases. The growth is driven by the boundary computation. The inside is an output of the computation, generated by the boundary quantum dynamics. The singularity is the limit of geometric representation, where complexity exceeds capacity. Each of these perspectives reveals a different aspect of what the inside truly is: a holographic projection, an error-corrected encoding, a quantum sum, a computational output. Each is valid within its own framework. Together, they paint a picture of the inside that is radically different from the classical picture. Not a fixed given region of space, but an emergent construction, built from quantum information and subject to dissolution at the Planck scale. The sixth approach is ER equals EPR, proposed by Leonard Susskind and Juan Maldacena in 2013. What physics tells us, through this conjecture, is that quantum entanglement and wormholes are the same phenomenon. The inside of the black hole is threaded with microscopic wormholes, connecting it to the outside through entanglement. The inside is not isolated. It is quantum mechanically connected to the exterior through the wormhole network. The connection between the inside and the emergence of spacetime provides the deepest theoretical perspective. If spacetime is emergent, the inside is not a pre-existing region of space. It is generated by quantum information and entanglement. The holographic principle says the inside is a projection of boundary physics. The error-correcting code says the inside is a redundant encoding. The computational complexity says the inside is a computational output. Each perspective reveals the inside as something derived, secondary, emergent from a more fundamental quantum description. The Ryu-Takayanagi formula connects entanglement on the boundary to geometry in the inside. The quantum version leads to the island formula. These formulas are the mathematical bridge between quantum information and the geometry of the inside. The inside is built from entanglement. It is sustained by error correction. It breaks when the code fails. The inside of a black hole is a mirror reflecting the fundamental nature of spacetime. If the inside is emergent, spacetime is emergent. If the inside is generated by information, spacetime is generated by information. If the inside is maintained by error correction, spacetime is maintained by error correction. What physics tells us about the inside is what physics tells us about reality at the deepest level. The seventh approach is black hole complementarity, introduced by Susskind, Thorlacius, and Uglum in 1993. What physics tells us, through complementarity, is that the inside looks different depending on who is asking. The outside observer sees information processed on the horizon. The falling observer sees a smooth interior. Both are correct. Neither is complete. The inside is observer-dependent. The eighth approach is computational complexity. Susskind proposed that the interior volume grows over time because the quantum computational complexity of the state increases. What physics tells us is that the inside is not static. It deepens, stretches, grows. The singularity is the point where the complexity exceeds the descriptive capacity of geometry. The ninth approach is causal set theory. Space-time is fundamentally discrete. The singularity cannot form in a discrete space-time. What physics tells us, through causal set theory, is that the inside has a minimum scale, a granularity that prevents infinite density. The 10th approach is asymptotically safe gravity. The gravitational coupling approaches a finite fixed point at high energies. The singularity is smoothed. What physics tells us is that the curvature remains bounded. The inside reaches extreme but finite conditions. The convergence across all these approaches is the most important thing physics tells us about the inside. Every approach agrees that the classical singularity does not exist. Every approach identifies the Planck scale as the resolution point. Every approach preserves information. Every approach suggests that the classical interior is an approximation of a deeper quantum reality. The math is striking. The Planck density is roughly 5.1 times 10 to the power of 96 kilograms per cubic meter. The Planck length is roughly 10 to the power of negative 35 meters. Every approach identifies these as the frontier. Below these scales, the classical description works. Above them, quantum gravity takes over. What physics tells us about the inside depends on which side of the frontier we are asking about. The connection between all these approaches and the nature of space-time provides the unifying perspective. Every proposal suggests that the smooth, continuous space-time of general relativity is an approximation that breaks down at the Planck scale. The inside of a black hole is where this approximation fails most dramatically. The singularity is the most extreme failure. But the entire interior, from the horizon to the center, is a region where the approximation is increasingly strained, increasingly unreliable, increasingly distant from the underlying quantum reality. The Ryu-Takayanagi formula, proposed in 2006, connects the entanglement entropy of boundary regions to the areas of minimal surfaces in the bulk. The quantum version includes quantum corrections and leads to the island formula. These formulas establish the mathematical connection between quantum information and space-time geometry. What physics tells us about the inside is encoded in these formulas. The inside is generated by entanglement, sustained by error correction, and subject to dissolution when the encoding fails. The gravitational path integral provides additional evidence. When all possible space-time geometries are summed, including contributions from replica wormholes, the result is finite and unitary. The singularity, present in individual classical geometries, is washed out in the quantum sum. The full quantum theory is singularity-free. What physics tells us about the inside, through the path integral, is that the classical singularity is an artifact of the classical approximation. The quantum sum produces finite answers. The Planck star provides the most concrete physical picture of what replaces the singularity at the center of the inside. The Planck star has the Planck density, roughly 5.1 times 10 to the power of 96 kilograms per cubic meter. It has a radius of roughly the Planck length, roughly 10 to the power of negative 35 meters. It is the smallest, densest possible configuration of matter. It preserves information, and it eventually transitions to a white hole, releasing everything that fell in. The black-to-white hole transition, explored by Haggard and Rovelli, connects the inside to a future outside. The matter that collapsed to form the black hole bounces at the Planck core and expands outward. The inside is not a dead end. It is a transit point. The information passes through the Planck scale bottleneck and re-emerges. The inside is temporary, not eternal. The thermodynamic constraints from the Bekenstein-Hawking entropy, the Hawking temperature, and the four laws of black hole mechanics must all be satisfied by any description of the inside. The exterior is finite and well-defined. The inside must be compatible. The singularity with its infinite density is incompatible. Something finite must replace it. The thermodynamics demands it. The Penrose-Hawking singularity theorems guarantee the singularity within classical general relativity. but the theorems require positive energy density, which quantum effects can violate at the Planck scale. The theorems guarantee the classical disease, but not the quantum one. Quantum gravity avoids the singularity by modifying the assumptions on which the theorems rest. The thermodynamic constraints from the Bekenstein-Hawking entropy, the Hawking temperature, and the four laws of black hole mechanics provide independent checks. The exterior is finite and well-defined. The inside must be compatible. A singularity of infinite density is incompatible with the finite exterior thermodynamics. What physics tells us about the inside is constrained by the thermodynamics of the outside. The observational constraints from gravitational wave astronomy tighten with each detection. Each merger tests general relativity in the strong field regime. The ring-down signals test the no-hair theorem. Future detectors, including LISA, the Einstein telescope, and Cosmic Explorer, will push sensitivity further. The Event Horizon telescope may resolve the photon ring. Each observation constrains what physics can tell us about the inside by testing the exterior predictions with increasing precision. The Penrose-Hawking singularity theorems guarantee the singularity within classical general relativity, but the theorems require positive energy density, which quantum effects at the Planck scale can violate. They require trapped surfaces, which quantum corrections can modify. The theorems guarantee the classical disease. They do not guarantee the quantum one. Change the framework, and the guarantee evaporates. The concept of geodesic incompleteness illustrates the nature of the classical failure. Geodesics terminate at the singularity. The spacetime has a boundary. The mathematical description cannot be extended. The inside in the classical picture has a finite temporal duration, ending at the singularity. The quantum resolution replaces this termination with something finite, something that geodesics can pass through or bounce off. The Hayden-Preskill protocol demonstrates that the inside returns information. Individual bits can be recovered after one scrambling time. The inside is not a permanent prison, it is a temporary processor. What physics tells us about the inside is that it is reversible, at least in the quantum mechanical sense. The information that goes in eventually comes out. And this is where the answer becomes deeply unsettling, because the convergence tells us what the inside is not. It is not a singularity of infinite density, but it does not tell us, with precision, what the inside is. The Planck scale resolution is a broad conclusion. The specific mechanism, the exact quantum degrees of freedom, the precise dynamics of the resolution remain the deepest open questions in physics. The deeper truth about what physics tells us about the inside of a black hole is that the inside may not be what we think it is. The classical picture of a smooth interior spacetime, with space and time inverted, and a singularity at the center, may be only an approximation. The deeper picture, emerging from the convergence of multiple theoretical approaches, is that the inside is emergent, derived, secondary to a more fundamental quantum description. The practical implications of what physics tells us about the inside extend far beyond astrophysics. Quantum error correction, inspired by holographic spacetime, is building fault-tolerant quantum computers. The holographic correspondence has applications in materials science, nuclear physics, and fluid dynamics. Tensor networks, inspired by the structure of holographic spacetime, have applications in machine learning and data compression. The thermodynamics of black holes has illuminated strongly coupled quantum systems. The observational constraints continue to tighten. Each gravitational wave detection tests general relativity near the inside's boundary. Each event horizon telescope image constrains the near-horizon geometry. Future detectors, including LISA, the Einstein telescope, and Cosmic Explorer, will push sensitivity further. The photon ring, if resolved, may encode quantum gravitational signatures. The philosophical implications are profound. Physics describes the inside through mathematics alone. No observation confirms the description directly. The power of mathematical extrapolation, the ability of equations tested in one regime to describe another, is one of the deepest features of science. The inside of a black hole is the most dramatic demonstration of this power. The connection between the inside and the nature of reality provides the deepest perspective. If the inside is emergent, generated by quantum information, then what physics tells us about the inside is what physics tells us about reality at the deepest level. The inside is a mirror, reflecting the fundamental nature of space-time and information and existence. The failure of general relativity at the singularity is, paradoxically, one of the theory's greatest achievements. By producing infinity at the center, the theory tells us precisely where it breaks down. The failure is not silent. It is loud, clear, mathematically precise. The theory writes its own limitations into its own equations, and these limitations point, with mathematical exactness, to the place where new physics must begin. We are beings made of atoms, living on a small planet, orbiting an ordinary star, in a galaxy whose center contains a supermassive black hole. We cannot visit the inside. We cannot observe it. We can only describe it with mathematics. And the description, while incomplete, is extraordinary. What physics tells us about the inside is one of the greatest intellectual achievements of our species. The evidence for this view comes from the holographic principle. The Bekenstein-Hawking entropy scales with area, not volume. If the fundamental degrees of freedom were distributed through the three-dimensional volume, the entropy would scale with volume. The fact that it scales with area suggests the three-dimensional interior is a projection of two-dimensional boundary physics. The inside is not independently real. It is generated by the boundary. Let that sink in. Mark van Ramsdonk showed in 2010 that entanglement generates spacetime. Reducing entanglement causes spacetime to disconnect. The inside of a black hole is held together by quantum correlations. When those correlations are disrupted, the inside falls apart. The inside is not a given, pre-existing region of space. It is a constructed region, built from entanglement, maintained by quantum correlations, and subject to dissolution when the correlations break. The error-correcting structure of holographic spacetime provides the mechanism. The inside is encoded in the boundary through a quantum error-correcting code. Away from the singularity, the code is robust. The inside is well-defined and reliable. Near the singularity, the code degrades. The encoding becomes unreliable. At the singularity, the code fails. The inside ceases to be well-defined. What physics tells us is that the inside has a shelf life, a range of validity, determined by the robustness of the encoding. The computational complexity perspective adds a dynamical dimension. The inside grows because the quantum complexity increases. Leonard Susskind proposed that the interior volume is proportional to the computational complexity of the quantum state. The inside is not static. It deepens over time, even after the black hole reaches thermal equilibrium from the outside perspective. What physics tells us is that the inside is alive, growing, evolving, generated by quantum computation. The scrambling time provides a temporal measure. For Sagittarius A star, the scrambling time is milliseconds. Within thousandths of a second of crossing the horizon, information is distributed across the entire boundary. The inside processes information at the maximum speed allowed by quantum mechanics. Patrick Hayden and John Preskill showed that black holes saturate the Margulis-Levitin bound on information processing speed. What physics tells us is that the inside is the fastest information processor in nature. The Wheeler-DeWitt equation adds a conceptual challenge. This equation, one of the earliest attempts at quantum gravity, has no time variable. The quantum state of the universe is static. Time must be reconstructed from internal correlations. What physics tells us, through the Wheeler-DeWitt equation, is that time itself may be emergent. The inside of a black hole, where classical time ends at the singularity, may be where the emergent nature of time is most visible. The connection between the inside and the arrow of time is profound. Black holes are the maximum entropy objects. The total entropy of all black holes dominates the cosmic entropy budget. The thermodynamic arrow of time points toward black holes. The inside is the endpoint of the thermodynamic journey, the place where entropy is maximized, where information is maximally scrambled, where the thermodynamic arrow has reached its target. But the information is not destroyed. The island formula confirms the page curve. Unitarity holds. The information that enters the inside is scrambled but preserved. The inside is not a graveyard for information. It is a processor, the fastest, most thorough processor in nature. What physics tells us is that the inside transforms information at the maximum possible rate and eventually returns it through the Hawking radiation over timescales that dwarf the current estimated age of the observable universe. The connection between the inside and the concept of observer complementarity provides the final perspective. The inside looks different depending on who is asking. The outside observer sees information processed on the horizon. The falling observer sees a smooth interior. Both are correct. Neither is complete. What physics tells us about the inside is observer-dependent. This observer-dependence challenges the assumption that there is a single, objective description of the inside. The inside, at the deepest level, may not have a single description. It may have complementary descriptions, each valid within its own domain, each incomplete, each consistent with quantum mechanics and thermodynamics. The concept of the Planck star connects the abstract theoretical proposals to a concrete physical picture. The singularity is replaced by a compact object at the Planck density. The Planck star has a radius of roughly the Planck length. It is the smallest, densest possible configuration. It preserves information. It eventually transitions to a white hole. The inside, at its most extreme, contains this kernel of quantum gravitational matter. The black to white hole transition provides a future for the inside. The collapsed matter bounces at the Planck core and expands outward. The inside is not permanent. It is transitional. The information passes through the Planck scale bottleneck and re-emerges. What physics tells us about the inside is that it has a beginning, a middle, and an end. The formation of the black hole, the quantum processing at the Planck core, and the emergence of the white hole. The connection between the inside and the problem of time is the deepest conceptual thread. The Wheeler-DeWitt equation has no time variable. Time is emergent. The inside, where time ends in the classical description, is where the emergence fails. But the quantum substrate persists. What physics tells us about the inside includes this. The temporal structure that we take for granted is emergent, not fundamental, and it is at the center of a black hole that this truth is most clearly revealed. The concept of black hole complementarity means that what physics tells us about the inside depends on the observer. The outside observer sees a different inside than the falling observer. Both descriptions are valid. Neither is complete. The inside is observer-dependent. This is one of the most radical implications of black hole physics. The deeper truth is that the inside of a black hole is not a fixed, given, objective region of space. It is an emergent construction, observer-dependent, informationally generated, computationally maintained, and subject to dissolution at the Planck scale. What physics tells us about the inside is a story about emergence, about information, about the deep quantum nature of reality. And the story, while incomplete, is the most extraordinary story physics has ever told. The connection between the inside and the problem of time adds depth. The Wheeler-DeWitt equation has no time variable. Time is emergent. The inside, where classical time ends at the singularity, is where the emergence fails. The timeless quantum substrate persists. The temporal output ceases. What physics tells us about the inside includes this. Time may not be fundamental. The Planck scale marks the boundary of our description. Below the Planck density, general relativity works. Above it, quantum gravity takes over. The Planck density, roughly 5.1 times 10 to the power of 96 kilograms per cubic meter, is the floor that replaces the classical infinity. What physics tells us about the inside, at the most extreme, is that it reaches this floor and stops, replaced by quantum physics we have not yet fully described. The Bekenstein-Hawking entropy formula, S equals A over 4 in Planck units, is the Rosetta Stone connecting gravity, thermodynamics, and quantum mechanics. It tells us the number of microscopic states of the inside, roughly 10 to the power of 77 for a solar mass black hole. Any description of the inside must accommodate this number. A true singularity cannot. The entropy demands structure. The singularity denies it. What physics tells us is that the entropy wins. The connection between the inside and the concept of the Planck scale is fundamental. The Planck length, the Planck time, the Planck density are the natural scales of quantum gravity. At these scales, the smooth spacetime description of general relativity breaks down. The inside, near the singularity, is where these scales are reached. What physics tells us about the inside depends on what physics operates at the Planck scale. The gap between the Planck scale and our experimental capabilities is roughly 17 orders of magnitude. No accelerator can reach Planck energies. No detector can resolve Planck lengths. What physics tells us about the inside at the Planck scale must come from theory, from mathematical consistency, from the constraints of the information paradox and black hole thermodynamics. The connection between the inside and the concept of information as the fundamental substance of reality provides the deepest perspective. If information is more fundamental than space-time, the inside of a black hole is not a region of space containing information. It is a region of information-generating space. The inside is made of information. The geometry is a secondary output. The singularity is where the output fails. The information persists. The Bekenstein bound sets the maximum information content of the inside. Black holes saturate it. The Margulis-Levitin theorem sets the maximum processing speed. Black holes saturate it. What physics tells us about the inside is that it is the ultimate quantum system, operating at every physical limit, storing and processing the maximum possible information at the maximum possible speed. The convergence of independent theoretical approaches provides confidence. String theory, loop quantum gravity, holographic duality, causal set theory, asymptotic safety, the gravitational path integral all agree the singularity is resolved at the Planck scale. Information is preserved. Space-time is emergent. These shared conclusions give us confidence that what physics tells us about the inside is approaching the truth. The connection between the inside and the emergence of time deserves final emphasis. The Wheeler-DeWitt equation has no time variable. Time is emergent. The inside, where classical time ends at the singularity, is where the emergence is most visible. What physics tells us about the inside includes this. Time may not be fundamental. It may arise from quantum information and entanglement. And at the center, where the emergence breaks down, the timeless quantum substrate continues. The Bekenstein bound sets the maximum information content. Black holes saturate it. The Margulis-Levitin theorem sets the maximum processing speed. Black holes saturate it. The inside is the most extreme quantum system in nature, operating at every physical limit simultaneously. It stores information at the maximum density allowed by the Bekenstein bound. It processes information at the maximum speed allowed by the Margulis-Levitin theorem. It scrambles information in the minimum time allowed by quantum mechanics. It generates entropy at the maximum rate consistent with the second law of thermodynamics. Every quantum limit is saturated. Every physical bound is reached. The inside of a black hole is the pinnacle of quantum dynamics, the most intense quantum system the laws of physics permit. What physics tells us about the inside is that it is the pinnacle of quantum dynamics. The Planck star provides a concrete picture of what replaces the singularity. The inside, at its most extreme, contains a compact object at the Planck density, the densest possible configuration of matter. The Planck star preserves information, has finite density, and eventually decays through a quantum transition. What physics tells us is that the inside has a flaw, a minimum scale, a Planck scale core that replaces the classical infinity with a quantum finite. The connection between the inside and the nature of consciousness is speculative but worth noting. Consciousness depends on information processing. The inside is the fastest information processor in nature. A falling observer, conscious and aware, would experience the inside firsthand, the only direct observation of the most extreme physics in the universe. Whether consciousness can persist through the Planck scale transition at the center is unknown. Whether the concept of experience has meaning without well-defined space-time is a question beyond current physics. The connection between the inside and the arrow of time adds cosmological weight. Black holes are the maximum entropy objects. The arrow of time points toward them. The inside is the thermodynamic endpoint. The total entropy of all black holes dominates the cosmic entropy budget at roughly 10 to the power of 104, compared to roughly 10 to the power of 88 for non-black hole matter. The inside is where the universe's entropy is concentrated. What physics tells us about the inside is connected to the deepest questions about the directionality of time. The Bekenstein bound sets the maximum information content of any region. Black holes saturate this bound. The inside contains the maximum possible information for its mass and energy. The Margulis-Levitin theorem sets the maximum processing speed. The inside operates at this limit. What physics tells us about the inside is that it is the most extreme quantum system in nature, operating at every physical limit simultaneously. The concept of the page time adds temporal structure. The page time is roughly the halfway point of evaporation. Before the page time, the entropy of the Hawking radiation rises. After it, the entropy falls. The page time marks the moment when information begins to emerge from the inside in earnest. What physics tells us about the inside is that its informational content is not trapped permanently. It is released, gradually, over the evaporation timescale. The concept of the quantum extremal island provides the mechanism of release. Islands are regions of the inside that belong informationally to the radiation. They grow as the black hole evaporates. By the end, the entire inside has been claimed by the islands. The inside is transferred informationally from the black hole to the radiation. What physics tells us about the inside includes this transfer mechanism. The inside does not die with the black hole. It is transferred to the radiation. Its information content is preserved. Let that sink in. The inside of a black hole does not disappear when the black hole evaporates. Its informational content is transferred to the Hawking radiation through the island mechanism. The inside lives on, encoded in the quantum correlations of the radiation, scrambled beyond any practical recovery, but preserved in principle by the laws of quantum mechanics. What physics tells us about the inside is that it is immortal, in the informational sense. The geometry may evaporate. The information does not. This is not science fiction. These are rigorous results within well-defined mathematical frameworks. The holographic principle is established through the AD-SCFT correspondence. The error-correcting structure is demonstrated. The island formula is derived. The page curve is reproduced. The convergence of independent approaches provides confidence. What physics tells us about the inside is emerging from the mathematics with increasing clarity. The deeper truth is that what physics tells us about the inside of a black hole is a story about the nature of spacetime itself. The inside is not a fixed, given region of space. It is an emergent construction, built from quantum information, generated by entanglement, maintained by error-correcting codes, and growing with computational complexity. The inside is not the container of physics, it is a product of physics. And at the center, where the classical product breaks down, the quantum physics that generates it continues, smooth and unitary, producing something finite where the classical picture produces infinity. What does it mean that physics can describe a place no one has ever seen? What does it mean that the mathematical equations that describe the orbits of planets and the bending of starlight also describe the inside of a black hole, a region forever sealed from observation? It means, first, that physics is more powerful than observation. The equations of general relativity do not stop at the event horizon. They continue inward, describing the geometry, the curvature, the tidal forces, the trajectory of every particle and every photon, with the same mathematical precision that they describe the exterior. The inside of a black hole is a prediction, a consequence of the mathematics, a region whose properties follow from the same equations that have been confirmed by decades of observations. What physics tells us about the inside is not speculation, it is extrapolation, mathematical extrapolation from a theory that has been verified to extraordinary precision. But extrapolation has limits. General relativity has been tested outside black holes at moderate curvatures. The inside involves extreme curvatures, approaching the Planck scale. The extrapolation from tested to untested regimes is enormous. 17 orders of magnitude in curvature separate the regime where general relativity has been tested from the regime where the singularity is predicted. What physics tells us about the ICE depends on how far we trust the extrapolation. There is a philosophical pause required here. Physics has always progressed by trusting mathematical extrapolation beyond the range of direct observation. Newton's laws, tested on Earth, were extrapolated to the orbits of planets. Maxwell's equations, tested in the laboratory, were extrapolated to electromagnetic waves propagating through the vacuum. Quantum mechanics, tested with atoms, was extrapolated to nuclei and particles. In each case, the extrapolation was vindicated. The mathematics worked beyond the range where it had been tested. The study of the inside has driven the development of quantum error correction, essential for fault-tolerant quantum computing. The holographic correspondence has applications in condensed matter physics, nuclear physics, and fluid dynamics. The thermodynamics of black holes has illuminated strongly coupled quantum systems. Gravitational wave astronomy has opened a new observational window. The most inaccessible place in the universe has generated some of the most practical tools in modern science. The next generation of observations will constrain what physics tells us about the inside. Each gravitational wave detection tests general relativity in the strong field regime. Each event horizon telescope observation constrains the near horizon geometry. Future detectors, ground-based and space-based, will push sensitivity further. The photon ring may be resolved. Each observation narrows the range of possible descriptions of the inside. The philosophical implications of what physics tells us about the inside are profound. Physics describes a place no one has ever seen. Mathematics reaches beyond observation. Equations do not stop at the event horizon. The power of mathematical extrapolation, the ability to describe the indescribable through equations tested elsewhere, is one of the deepest features of physics. The inside of a black hole is the most dramatic demonstration of this power. The study of the inside has generated advances across physics and technology. Quantum error correction for quantum computing, holographic methods for condensed matter physics, scrambling dynamics for quantum simulation, tensor networks for machine learning, gravitational wave astronomy. Each was driven by the attempt to understand the inside. The mathematical tools are remarkable. The Ryuta-Kayanagi formula connects entanglement to geometry. The island formula connects evaporation to unitarity. The error-correcting code connects redundancy to spacetime stability. The computational complexity connects growth to volume. Each tool was developed for the inside and has found applications elsewhere. The philosophical implications are equally profound. Physics describes the inside through mathematics. The equations do not stop at the event horizon. They continue inward, producing predictions about a region no observer can access. The power of mathematical extrapolation is demonstrated by the inside more dramatically than by any other domain in science. The study of the inside has revealed connections between physics and pure mathematics that no one anticipated. Penrose introduced topological methods to general relativity. The holographic principle connected Riemannian geometry to information theory. AD-SCFT connected hyperbolic geometry to conformal field theory. Error correction connected coding theory to differential geometry. Each connection was unexpected. Each enriched both fields. The inside has been one of the most productive catalysts for interdisciplinary collaboration in the history of science. General relativists, particle physicists, string theorists, loop quantum gravity researchers, quantum information scientists, mathematicians, and computer scientists have all been drawn to the same fundamental question. What is inside? The result has been a flowering of ideas that extends far beyond the original question. The practical technologies that have emerged continue to grow. Quantum error correction for quantum computing, tensor networks for machine learning, holographic methods for materials science, scrambling dynamics for quantum simulation. Each application traces its origins to the study of the inside. The most inaccessible place in the universe has generated tools that are transforming science and technology. The next generation will have tools we cannot imagine. Quantum computers capable of simulating aspects of quantum gravity, improved gravitational wave detectors, refined theoretical frameworks. The complete description of the inside may come from any of these, or from a direction no one has yet anticipated. The connection between the inside and the deepest questions about reality provides the ultimate motivation. What is spacetime, made of? Is information fundamental? Is time emergent? What does it mean for something to exist at the most basic level? These questions converge at the inside of a black hole. The answers will come from understanding the inside, and the answers will transform our understanding of everything. The inside of a black hole confronts us with the limits of knowledge. We cannot observe it. We cannot probe it. We must rely entirely on theory. And theory, for the first time in the history of physics, faces a situation where two extraordinarily successful frameworks contradict each other. The inside is the frontier of understanding, the boundary between the known and the unknown, the place where the deepest questions about the nature of reality become unavoidable. But the theoretical reasoning has been remarkably productive. The information paradox, the firewall, the holographic principle, the island formula, quantum error correction, computational complexity, all were discovered or sharpened through the study of the inside. The most inaccessible place has generated the deepest insights. The boundary between the known and the unknown has been the most fertile ground for new ideas. The next generation of physicists will inherit this frontier. They will have quantum computers, improved detectors, refined frameworks. The resolution of what physics tells us about the inside may come from a direction no one currently anticipates, but it will come. Human curiosity does not accept permanent boundaries. The connection between the inside and the nature of reality provides the ultimate perspective. If the inside is emergent, if it is generated by quantum information, if it is sustained by error-correcting codes, if it grows with computational complexity, then what physics tells us about the inside is a statement about the nature of reality at the deepest level. The inside is a mirror reflecting the fundamental nature of spacetime, information, and existence. But in each case, the extrapolation had eventually reached a boundary. Newton's laws failed at the speed of light. Classical electromagnetism failed at the atomic scale. Each failure was a signal that new physics was needed. The failure of general relativity at the singularity is the latest such signal. What physics tells us about the inside through the singularity is that the current mathematical framework has reached its boundary. New physics, quantum gravity, is needed to describe what lies beyond. The practical implications of what physics tells us about the inside have been substantial. The study of the inside has driven the development of the holographic principle, the AD-SCFT correspondence, quantum error correction, the island formula, and the connection between entanglement and geometry. Each represents a major advance. Each was motivated by the attempt to understand the inside. The observational landscape continues to evolve. Gravitational wave detectors have observed roughly 90 events. The Event Horizon Telescope has photographed 2 supermassive black hole shadows. Future detectors will provide more precise measurements. The photon ring may be resolved. Space-based detectors like LISA will detect supermassive mergers. Each observation constrains what physics tells us about the inside by testing the exterior predictions of general relativity with increasing precision. The mathematical tools developed for the inside have found applications across science. Quantum error correction for quantum computing, holographic methods for condensed matter physics, scrambling dynamics for quantum simulation, tensor networks for machine learning. The most inaccessible place in the universe has generated some of the most practical tools in modern science. The connection between the inside and the nature of reality provides the deepest implication. If the inside is emergent, if it is generated by quantum information and entanglement, then what physics tells us about the inside is a statement about the nature of reality at the deepest level. The inside is where the emergent nature of space-time is most visible, where the classical picture breaks down and the quantum picture shows through. What physics tells us about the inside is, ultimately, what physics tells us about everything. The failure of general relativity at the singularity is, paradoxically, one of the theory's greatest achievements. By producing infinity at the center, the theory tells us precisely where it breaks down. The failure is not silent. It is loud, clear, mathematically precise. The theory writes its own limitations into its own equations, and these limitations point, with mathematical exactness, to the place where new physics must begin. We are beings made of atoms, held together by electromagnetic forces, living on a small planet orbiting an ordinary star in a galaxy that contains a supermassive black hole at its center. We cannot visit the inside. We cannot observe it. We can only describe it with mathematics, constraining it with theory, approaching it with the most powerful intellectual tools our species has developed. The fact that we can do this, that finite minds on a terrestrial surface can describe the inside of a black hole with mathematical precision, is itself one of the most remarkable facts about the universe. What physics tells us about the inside of a black hole is extraordinary. It tells us that space and time exchange their roles, that the center is a moment in the future, not a place in space, that the geometry collapses, the tidal forces grow, the curvature increases without bound, that the singularity, where the mathematics breaks, is almost certainly not real, that quantum mechanics demands something finite at the center, that information is preserved, that the inside may be emergent, generated by entanglement, maintained by error-correcting codes, growing with computational complexity. Physics tells us all of this without anyone ever seeing the inside, without a single instrument crossing the event horizon, without a single photon escaping to carry the message outward. Physics tells us, through mathematics, through the power of equations tested elsewhere and extrapolated to the most extreme conditions the universe can produce. The story has many chapters: the Schwarzschild solution of 1916, the Kerr solution of 1963, the Penrose singularity theorem of 1965, the Hawking radiation of 1974, the holographic principle of 1993, the ADS-CFT correspondence of 1997, the firewall paradox of 2012, the island formula of 2019 and 2020. Each chapter has added to what physics tells us. Each has deepened the picture. Each has brought us closer to understanding the most inaccessible place in the cosmos. The convergence of independent theoretical approaches provides the strongest evidence about the inside. String theory, loop quantum gravity, holographic duality, causal set theory, asymptotic safety, the gravitational path integral all agree. The singularity is not real. The Planck scale is the resolution point. Information is preserved. Spacetime is emergent. These shared conclusions, reached by independent approaches from independent starting points, give us confidence that what physics tells us about the inside is approaching the truth. What physics tells us about the inside of a black hole is also what physics tells us about reality at the deepest level. The inside is where space-time is most extreme, where gravity is strongest, where quantum effects are most important, where the classical description fails and the quantum description must take over. Understanding the inside means understanding the transition from the classical to the quantum, from the emergent to the fundamental, from the geometric to the informational. The theory of quantum gravity, when it is finally written, will tell us what the inside truly is. It will resolve the singularity. It will preserve information. It will reproduce the Bekenstein-Hawking entropy. It will be consistent with the Page curve. It will describe the emergence of spacetime from quantum information. And it will, for the first time, give us a complete and reliable picture of the most inaccessible place in the universe. Somewhere right now, a physicist is working toward this picture, staring at equations, running simulations, turning ideas over. The inside of a black hole does not know it is being studied. It does not care whether we understand it. It is simply there, behind the event horizon, obeying whatever laws govern it, whether those laws are the classical laws of general relativity or the quantum laws that we have not yet fully written. What physics tells us about the inside of a black hole is the most profound story science has ever told. A story of mathematics pushed to its limits, of theories that work everywhere except at one point, of a conflict between two frameworks that has driven 50 years of progress, of an inaccessible place that has generated some of the deepest insights into the nature of reality. The inside of a black hole is the universe's most closely guarded secret. Physics has been working to uncover it for more than a century. The work is not finished, but what physics has told us so far is extraordinary, and what physics will tell us next, when quantum gravity is finally understood, will be more extraordinary still. The study of what physics tells us about the inside has driven some of the most important advances in theoretical physics. The information paradox launched black hole thermodynamics. The holographic principle transformed gravity. AD-SCFT became the most powerful tool in theoretical physics. The firewall paradox sharpened the crisis. The island formula provided the breakthrough. Quantum error correction connected black holes to quantum computing. Each advance was driven by the attempt to understand the inside. The resolution of what the inside truly is will have implications far beyond black holes. It will provide the mathematical language for the very early universe. It will connect gravity to the other forces. It will reveal the nature of space-time at the Planck scale. It will answer the deepest questions about the fabric of reality. The history of physics is a history of sealed regions opened by mathematics. Newton opened the interior of the solar system through calculus. Maxwell opened the interior of electromagnetic waves through his equations. Schrödinger opened the interior of the atom through his wave equation. General relativity opened the interior of black holes through Einstein's field equations. The next opening, the opening of the quantum interior, will require the equations of quantum gravity. Those equations are being assembled, piece by piece, constraint by constraint, insight by insight. The opening is coming. The mathematical tools have applications across science. Quantum error correction for fault-tolerant quantum computing. Tensor networks for machine learning and data compression. Holographic methods for strongly coupled materials. Scrambling dynamics for quantum simulation. The most inaccessible place in the universe has generated practical technologies. The philosophical dimension deserves reflection. Physics describes the inside through mathematics, not observation. This is remarkable. It shows that mathematics has a reach that extends beyond what can be seen, touched, or measured. The equations describe the inside because the equations are the same equations that describe the outside, and the equations do not stop at the horizon. The power of mathematical extrapolation is one of the deepest features of physics. The next generation of physicists will have tools we cannot imagine. Quantum computers, improved gravitational wave detectors, refined theoretical frameworks. The resolution of what physics tells us about the inside may come from any of these directions, or from a direction no one has yet anticipated. The connection between the inside and the nature of reality provides the deepest perspective. If the inside is emergent, what physics tells us about the inside is a statement about emergence. If information is fundamental, what physics tells us about the inside is a statement about information. If entanglement generates spacetime, what physics tells us about the inside is a statement about entanglement. The inside of a black hole is not just a place, it is a mirror, reflecting the deepest truths about the nature of existence. The inside waits, silent, sealed, absolute, and physics keeps reaching toward it. Because that is what physics does. It reaches toward the unreachable. It describes the indescribable. It tells us about the places we can never go, the things we can never see, the truths we can never directly verify. And in doing so, it reveals the deepest nature of the universe. Every revolution in physics has been triggered by a boundary between the known and the unknown. The boundary between classical and relativistic mechanics at the speed of light triggered special relativity. The boundary between classical and quantum at the atomic scale triggered quantum mechanics. The boundary between Newtonian and Einsteinian gravity at extreme curvatures triggered general relativity. The event horizon of a black hole is the latest and deepest such boundary, and what physics tells us about the region beyond it will trigger the next revolution. The theory of quantum gravity, when it is finally written, will be the complete description of the inside. It will resolve the singularity, preserve information, reproduce the entropy, be consistent with the page curve, describe the emergence of spacetime from quantum information, and it will tell us, for the first time, what the inside of a black hole truly is. The resolution will have implications far beyond black holes. It will provide the mathematical language for describing the very early universe, when conditions may have resembled the inside of a black hole. It will connect gravity to the other fundamental forces. It will reveal the nature of space-time at the Planck scale. And it will answer the question that has driven 50 years of theoretical physics. What is inside? The answer is coming. Not today. Perhaps not for decades. But the convergence of independent approaches provides confidence. The theoretical tools are improving. The observational constraints are tightening. The direction is clear. The singularity does not exist. Space-time is emergent. Information is preserved. The inside is quantum. The inside waits, patient beyond all measure, at the center of every black hole in the cosmos, the deepest secret in the darkest place, behind the most impenetrable boundary. And physics, undaunted, keeps talking, keeps calculating, keeps reaching toward the truth. Because physics does not accept boundaries as permanent. Physics treats them as challenges. And the event horizon, the most absolute boundary in nature, is the greatest challenge physics has ever faced. The inside waits. And physics keeps talking, because physics never stops. Not at the event horizon, not at the singularity, not at the Planck scale, not at the limits of observation, not at the boundaries of understanding. Physics keeps talking, keeps calculating, keeps reaching, keeps discovering. And the inside of a black hole, the most inaccessible place in nature, keeps listening. Because physics never stops talking. It describes what it can, reaches for what it cannot, and pushes forward, always, toward the truth. The truth about the inside of a black hole. The truth about the nature of space-time. The truth about reality at its deepest level. And when physics finally tells us the complete story of the inside, it will be the most extraordinary story ever told. A story about a place no one has ever seen. Described by equations no experiment can directly verify. Revealing truths no observation can directly confirm. The most inaccessible story about the most inaccessible place. The most important predictions about the most extreme conditions. The most profound insights about the most fundamental questions, told by the most powerful tool the human mind has ever developed. The language of mathematics, reaching into the darkness, bringing back the light. The inside of a black hole has never been seen. It may never be seen. But physics has described it, and the description, extraordinary in its precision, profound in its implications, and transformative in its consequences, will stand as one of the great achievements of the human mind for as long as minds exist to contemplate it. No human being has ever seen the inside of a black hole. No instrument has ever measured it. No probe has ever returned from it. No signal of any kind has ever escaped from behind the event horizon to tell us what lies within. The inside of a black hole is the most completely inaccessible place in the observable universe. It is sealed off from the rest of reality by a causal boundary so absolute that not even light, the fastest thing in existence, can cross it outward. The event horizon is the ultimate one-way door. You can go in, you can never come out. And once inside, you can never send a message, a signal, a single photon back to the universe you've left behind. And yet, physics tells us what is inside, not through observation, not through experiment, through mathematics, through the extraordinary power of general relativity. The theory of gravity published by Albert Einstein in 1915, confirmed by more than a century of observations, and verified to a precision that exceeds any other theory in the history of science. General relativity describes the inside of a black hole with the same mathematical precision that it describes the outside. The equations do not stop at the event horizon. They continue inward, describing the geometry of space-time, the behavior of matter, the structure of reality inside the black hole, with the same exactness that they describe the bending of starlight or the precession of Mercury's orbit. But the story that physics tells about the inside of a black hole is deeply strange. It is a story of inverted dimensions, of collapsing geometry, of chaotic oscillations, of a destination that is not a place but a time, and of a center where the mathematics itself breaks down and produces infinity. It is a story that, when combined with quantum mechanics, becomes a paradox, a contradiction between our two greatest theories that has consumed the most brilliant minds in physics for more than 50 years. According to current scientific estimates, the observable universe contains on the order of 100 billion galaxies, each harboring at least one supermassive black hole and potentially hundreds of millions of stellar mass black holes. Sagittarius A star, at the center of our Milky Way, has roughly 4 million solar masses. M87 star has roughly 6.5 billion solar masses. Every one of these objects has an inside, a region of spacetime forever hidden from view, described by the equations of general relativity and containing the most extreme physical conditions in the universe. By the end of tonight, you are going to understand what physics tells us about the inside of a black hole. You are going to follow the journey from the event horizon to the singularity. You are going to learn how space and time exchange their roles, why the center is a moment in the future rather than a place in space, what the quantum corrections to the classical picture look like, and why the inside of a black hole may hold the key to the deepest secrets of reality. The scope of the mystery extends across the cosmos. Every supermassive black hole at the center of every galaxy has an inside that physics describes but no observer can visit. Every stellar mass black hole, remnant of a massive star, has an inside that our equations characterize but our instruments can never probe. The number of these interiors is beyond meaningful count. Hundreds of millions per galaxy, hundreds of billions of galaxies. The inside of a black hole is not a rare curiosity. It is one of the most common features of the cosmic landscape, repeated trillions of times across the observable universe, each instance containing the same extreme physics, the same mathematical predictions, the same unresolved mysteries. The inside is the testing ground for the deepest ideas in physics. The holographic principle, the information paradox, the firewall, the island formula, quantum error correction, computational complexity, all of these have been developed and refined through the study of the inside. The most inaccessible place has driven the most important theoretical advances. Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. The inside of a black hole is the most extreme environment physics can describe. It is the place where gravity is strongest, where space-time is most curved, where the known laws of physics are pushed to their absolute limits, and, at the center, beyond their limits. It is the place where the conflict between general relativity and quantum mechanics is most acute, where the deepest questions about the nature of space, time, information, and reality converge. What physics tells us about this place is extraordinary. What physics cannot yet tell us is even more so. The inside of a black hole is also deeply personal. If you fell into a supermassive black hole, you would cross the event horizon without noticing. Your clock would tick normally, your thoughts would flow, and you would fall, for seconds or minutes or hours depending on the mass, through a region of space-time that physics describes with extraordinary precision but that no one has ever observed. You would be the first witness to the inside, the first observer of the place where space and time exchange their roles. The first person to see the singularity, or whatever replaces it in the quantum theory. And you could never report your findings. The event horizon ensures that your discovery dies with you. The most profound observation in the history of science would be witnessed by someone who can never share it. The inside is also connected to the most fundamental questions about the cosmos. The initial singularity of cosmological models shares mathematical properties with the singularity inside a black hole. Resolving one may resolve the other. What physics tells us about the inside of a black hole may also tell us about the origin of the universe. Now let us begin. To understand what physics tells us about the inside of a black hole, we must first understand the physics itself, the tools and theories that allow us to describe a place no one has ever seen. We must understand general relativity, its mathematical framework, its extraordinary successes, and the precise predictions it makes about the interior. And we must understand quantum mechanics, the theory that challenges those predictions and demands a deeper answer. General relativity describes gravity as the curvature of spacetime caused by mass and energy. The mathematical framework is differential geometry on smooth manifolds. The central equations are Einstein's field equations, 10 coupled nonlinear partial differential equations relating the geometry of spacetime to the distribution of mass and energy. These equations are extraordinarily difficult to solve, but the solutions that have been found describe the universe with breathtaking precision. The first solution was found by Karl Schwarzschild in 1916. Months after Einstein published his theory, Schwarzschild was serving on the Eastern Front of the First World War, suffering from a fatal autoimmune disease. He solved Einstein's equations for the simplest case, a non-rotating, uncharged, spherical mass in vacuum. His solution describes the complete spacetime geometry around and inside such an object. The Schwarzschild solution contains two remarkable features. At the Schwarzschild radius, an event horizon forms, a boundary from which nothing can escape. At the center, a singularity forms, a point of infinite density where the curvature diverges. These two features define the mathematical structure of the non-rotating black hole and determine everything physics can tell us about its inside. The Schwarzschild radius depends only on mass. For our Sun, it is roughly 1.86 miles. For the Earth, roughly 9 millimeters. For Sagittarius A star, roughly 7.5 million miles. For M87 star, roughly 12 billion miles, larger than the orbit of Pluto. The event horizon is where physics tells us the inside begins. Everything beyond this radius, from the perspective of an outside observer, is the interior, the sealed region from which no information escapes. The observational evidence for black holes is overwhelming. The X-ray binary Cygnus X-1 was identified as a strong candidate in 1971. The LIGO Observatory detected gravitational waves from merging black holes in 2015, designated GW150914. The two black holes had masses of roughly 36 and 29 solar masses. Their merger released roughly 3 solar masses of energy as gravitational waves, briefly outshining the combined light of every star in the observable universe. The Event Horizon Telescope photographed the shadow of M87 star in 2019 and Sagittarius A star in 2022. Andrea Ghez and Reinhard Genzel shared the Nobel Prize in 2020 for tracking stars orbiting Sagittarius A star. Roughly 90 gravitational wave events have been observed by the LIGO-Virgo-Cagra collaboration. Each observation confirms that black holes exist and that their exteriors match the predictions of general relativity. None tells us directly about the inside. The event horizon ensures that the inside remains permanently hidden. Everything physics tells us about the interior comes from theory, from the mathematical extrapolation of the equations that work so well outside. Now, what does the Schwarzschild solution tell us about the inside? The concept of gravitational time dilation provides one of the most dramatic demonstrations of what physics tells us about the region near the inside. As an observer approaches the event horizon, their clock slows relative to a distant observer. At the horizon itself, time stops completely from the outside perspective. The falling observer, however, experiences nothing unusual. Their clock ticks normally. They cross the horizon in finite time by their own measurement. Two observers, two experiences, two completely different accounts of the same event. This divergence in temporal experience is not a paradox. It is a consequence of the relativity of time, Einstein's deepest insight. The accretion process illustrates how matter enters the inside. Gas and dust spiral inward through an accretion disk, heated by friction to millions or billions of degrees. The disk can outshine an entire galaxy. Active galactic nuclei, quasars and blazars are all powered by matter falling toward the event horizon. Up to roughly 40% of the rest mass energy is radiated before the matter crosses the horizon. Once inside, the matter falls toward the singularity, carrying its quantum state with it. The inside accumulates the information of everything that has ever crossed the horizon. The Blandford-Znajek process shows how magnetic fields threading the ergosphere of a rotating black hole can extract rotational energy and launch relativistic jets extending hundreds of thousands of light years. These jets, the most powerful sustained energy sources in the universe, are powered by the region just outside the inside. The inside is the heart of a cosmic engine of extraordinary power. The relationship between the event horizon and the inside is mediated by the concept of causal structure. In general relativity, every event has a light cone, the set of all future and past directions along which light can travel. Outside the event horizon, the light cones point outward. Light can escape, information can be transmitted. At the event horizon, the light cones tilt so that the outward direction is no longer in the future cone. Inside, every light cone points toward the center. The entire inside is causally connected only to the singularity. The causal structure defines the inside as the region from which no causal influence can reach the outside. The concept of the apparent horizon, distinct from the event horizon, provides additional insight. The event horizon is global, defined by the asymptotic structure of spacetime. The apparent horizon is local, defined by the convergence of outgoing light rays. For a static black hole, the two coincide. For a dynamic black hole, they differ. During the collapse that forms the black hole, the apparent horizon forms first. The event horizon forms later. The inside, defined by the event horizon, is a global concept requiring knowledge of the entire future evolution of the spacetime. The concept of the Penrose diagram reveals the causal structure with particular clarity. The inside is a diamond-shaped region, bounded by the horizon below and the singularity above. Every future-directed world line from inside must terminate at the singularity. The Penrose diagram makes the inevitability of the singularity visually obvious. There is no path through the diamond that avoids the upper boundary. The density gradient inside the black hole varies enormously. Near the horizon of a supermassive black hole, the density is comparable to water or air. As the observer falls deeper, the effective curvature increases. The tidal forces grow. Near the singularity, every quantity diverges. The inside is not uniform. It is a gradient, a transition from gentle to extreme, from well understood to mysterious, from the domain of tested physics to the frontier of the unknown. The Unruh effect, discovered by William Unruh in 1976, connects the physics of the inside to the physics of acceleration. An accelerating observer in flat spacetime perceives a thermal bath at a temperature proportional to the acceleration. The Hawking temperature is the gravitational analog. The equivalence principle connects the two. The inside, where gravity is extreme, is connected to the fundamental quantum vacuum through these equivalences. The first thing physics tells us is that the event horizon is not a physical barrier. It is not a wall. It is not a surface. It is not made of anything. It is a mathematical boundary defined by the causal structure of spacetime. A freely falling observer crosses the event horizon without feeling anything unusual. For a supermassive black hole like Sagittarius A star, the tidal forces at the horizon are negligible. The observer would not know the moment of crossing. No alarm would sound. No sensation would mark the transition. The event horizon is invisible. This invisibility is confirmed by the equivalence principle, one of the foundational principles of general relativity. The equivalence principle states that the local physics of a gravitational field is equivalent to the local physics of acceleration. Near the event horizon, the local physics is indistinguishable from the physics experienced by an accelerating observer in flat space-time. The horizon is locally unremarkable. The drama is global. Once inside, every possible path leads deeper. The second thing physics tells us is gravitational time dilation. As an object approaches the event horizon, time slows down relative to a distant observer. At the horizon itself, time, as measured by the distant observer, stops completely. The falling observer appears to freeze, redshift dim, and eventually vanish, a ghost image lingering at the edge of the horizon for all eternity. From the distant observer's perspective, nothing ever crosses the event horizon. The crossing takes infinite time. The formation of stellar mass black holes through supernova explosions connects the inside to the life cycle of stars. When a star more than roughly 20 to 25 solar masses exhausts its nuclear fuel, the core collapses. The outer layers are expelled. If the remnant core exceeds roughly 3 solar masses, no known force can halt the collapse. The matter contracts past the Schwarzschild radius. The event horizon forms, and the inside begins. This process has occurred billions of times throughout cosmic history. Supermassive black holes, with masses of millions to billions of solar masses, have a different formation history. They may have formed from the direct collapse of massive gas clouds, from the growth of smaller seeds through accretion, or from the mergers of smaller black holes. The inside of a supermassive black hole contains the accumulated matter of millions of years of accretion. Stars, gas, dust, photons, gravitational waves, everything that has ever crossed the horizon. The M-sigma relation, the correlation between black hole mass and stellar velocity dispersion, shows that the growth of the black hole and the galaxy are linked. the inside of the central supermassive black hole has been shaped by the galaxy's history. The inside is a repository of the galaxy's past. But from the falling observer's perspective, the crossing happens in finite time. Their clock ticks normally. Their heartbeat continues. They cross the horizon and continue to fall. The disagreement between the two observers is not a contradiction. It is a consequence of the relativity of time, the fundamental insight of Einstein's theory. Time is not absolute, it is relative, and at the event horizon, the relativity reaches its extreme. One observer sees finite, the other sees infinite time. The density at the event horizon varies enormously with mass. For a stellar mass black hole of 10 solar masses, the average density at the horizon is roughly 200 million tons per cubic centimeter. For Sagittarius A star, roughly 1,000 kilograms per cubic centimeter. For M87 star, less than the density of air. The larger the black hole, the gentler the horizon. You could cross the event horizon of M87 star surrounded by spacetime less dense than the atmosphere of the Earth. The tidal forces at the horizon also vary with mass. For a stellar mass black hole, the tidal forces are extreme, strong enough to spaghettify a human body. For a supermassive black hole, they are negligible. The most absolute boundary in the universe is, for sufficiently large black holes, the most gentle. The third thing physics tells us begins at the event horizon and defines the entire interior. Inside the black hole, space and time exchange their mathematical roles. The radial direction, which outside the horizon is a spatial direction you can move along freely, becomes time-like inside. The time direction, which outside flows from past to future, becomes space-like inside. The metric tensor, the mathematical object encoding the geometry of space-time, changes the signs of its temporal and radial components at the horizon. This exchange is the most important thing physics tells us about the inside of a black hole. It means the singularity at the center is not a place in space. It is a moment in time, a future moment, as inevitable as tomorrow. The singularity is not something you are falling toward through space. It is something you are aging toward through time. Every path inside the black hole leads to the singularity, because the singularity is in the future, and the future cannot be avoided. The proper time from the event horizon to the singularity depends on their mass. For a stellar mass black hole of 10 solar masses, roughly a tenth of a millisecond. For Sagittarius A star, roughly 20 seconds. For M87 star, possibly hours. For the most massive known black holes, exceeding 10 billion solar masses, the time could be many hours. These are the durations of existence inside a black hole, the window between crossing the horizon and reaching the singularity. The photon sphere, at 1.5 Schwarzschild radii, is the last stable orbit for light. At this radius, photons can circle the black hole. Inside the photon sphere, no stable circular orbit exists for either light or matter. The innermost stable circular orbit for massive particles is at 3 Schwarzschild radii. Inside this radius, all matter must fall inward or escape outward. These boundaries define the transition from the exterior, where physics is well tested and directly observable, to the interior, where physics can only be inferred. The concept of the trapped surface is the mathematical trigger for the singularity. A trapped surface is a closed two-dimensional surface from which all light rays, even outgoing ones, converge inward. Inside the event horizon, every sphere is a trapped surface. The existence of a trapped surface, combined with positive energy and general relativity, guarantees the singularity according to Penrose's theorem. The Kruskal C coordinates reveal the maximal analytic extension of the Schwarzschild spacetime. The event horizon is smooth. The full causal structure is visible. The Penrose diagram compresses the spacetime into a finite picture, showing the inside as a diamond-shaped region, bounded by the horizon and the singularity. Every future-directed path from any point inside ends at the singularity. The relationship between the inside and the concept of frame dragging provides insight into rotating black holes. A rotating black hole drags spacetime around with it. In the ergosphere, the region between the static limit and the event horizon, spacetime is dragged so violently that no object can remain stationary. Everything must co-rotate. Inside the event horizon, the frame dragging is even more extreme. The geometry of the inside is not just curved. It is twisted, wrapped, dragged by the rotation of the black hole. The angular momentum of the black hole affects the structure of the inside. The Kerr solution, which describes a rotating black hole, has a more complex interior than the Schwarzschild solution. The two horizons, the ring singularity, the Cauchy horizon, all depend on the angular momentum. For maximally rotating black holes, the event horizon shrinks and the ergosphere expands. The inside of a rotating black hole is a different physical environment from the inside of a non-rotating one. The charge of a black hole also affects the inside. The Reissner-Nordstrom solution describes a charged, non-rotating black hole. Like the Kerr solution, it has two horizons and a more complex interior. The Kerr-Newman solution describes a charged, rotating black hole, the most general stationary black hole solution. Real astrophysical black holes are expected to be nearly uncharged because plasma in the accretion disk neutralizes any charge quickly. But the mathematical structure of the charged solutions provides valuable insight into the general features of black hole interiors. The strong cosmic censorship conjecture claims that the inside beyond the Cauchy horizon of a rotating black hole is indeterminate. Determinism fails. Recent work in de Sitter spacetimes has found that this conjecture may be violated under certain conditions. If so, the inside of a rotating black hole may involve genuine indeterminism, with multiple possible futures branching from the same past. The membrane paradigm, developed by Kip Thorne and collaborators, describes the event horizon as a physical membrane with viscosity, conductivity, and temperature. This membrane processes information, absorbs matter, and radiates. The membrane is the gateway to the inside, the active boundary through which everything must pass to enter the sealed interior. The Strominger-Vafa counting provided the first microscopic accounting of black hole entropy in string theory. For certain extremal black holes, the microstate count matches the Bekenstein-Hawking formula exactly. This proves that the inside has genuine microscopic structure, genuine quantum states, that the entropy is real and countable. The No-Hair theorem states that a black hole is completely characterized by three quantities: mass, charge, and spin. All other information about what form the black hole is hidden inside, behind the event horizon. The exterior is radically simple, 3 numbers. The interior is radically complex. The Bekenstein-Hawking entropy tells us the black hole has roughly 10 to the power of 77 microscopic states for a solar mass object. The gap between the 3-number exterior and the 10 to the 77 state interior is the information gap, one of the deepest puzzles about the inside. The relationship between the inside and the Hawking radiation provides crucial thermodynamic constraints. Hawking showed in 1974 that quantum effects near the event horizon produce thermal radiation with a temperature inversely proportional to the mass. For a solar mass black hole, the temperature is roughly 60 billionths of a Kelvin. The evaporation time is roughly 10 to the power of 67 years. The thermal nature of the radiation creates the information paradox. The radiation carries no information about what fell in. If the black hole evaporates completely, all information about the inside is lost. Unitarity is violated. Most physicists believe information is preserved. The Island formula, developed in 2019 and 2020, confirmed that the entropy of the radiation follows the Page curve, the signature of unitary evolution. The Page curve provides the definitive test of information preservation. Don Page showed in 1993 that if evolution is unitary, the entropy of the radiation rises during the first half of evaporation and falls during the second half. The Page time, roughly the halfway point, is when information begins to emerge from the inside. The Island formula reproduces this curve. Information survives the inside. The relationship between the event horizon and the photon sphere provides observational context. The photon sphere, at 1.5 Schwarzschild radii, is where light can orbit. The photon ring, a predicted sharp, bright feature formed by photons that have orbited multiple times, encodes geometric information about the near-horizon spacetime. Future event horizon telescope observations may resolve this feature, providing constraints on the geometry of the region just outside the inside. What physics tells us about the inside begins with what we can observe just outside it. The Hayden-Preskill protocol shows how quickly individual bits can be recovered from the radiation. For Sagittarius A star, the scrambling time is milliseconds. After one scrambling time, a bit thrown into an old black hole can be recovered from the subsequent radiation. The inside processes information at the maximum quantum rate and returns it. The inside is not a permanent prison. It is a temporary maximum rate processor. The scrambling dynamics provide the temporal heartbeat of the inside. The Margolis-Levitin theorem sets the absolute maximum speed of quantum evolution for a system of given energy. Black holes saturate this bound. The inside operates at the physical limit. No system, real or theoretical, can process information faster. What physics tells us about the inside includes this. It is the pinnacle of quantum dynamics. The concept of the trapped surface is central to understanding why the inside must contain a singularity within the framework of general relativity. A trapped surface is a closed two-dimensional surface from which all outgoing light rays are converging inward. Inside the event horizon, every sphere is a trapped surface. All light, even outgoing light, is heading inward. The existence of a trapped surface, combined with the positivity of energy and the validity of general relativity, guarantees the formation of a singularity, according to Penrose's theorem. The Kruskal-Sekeri's coordinates provide the maximal analytic extension of the Schwarzschild spacetime. In these coordinates, the event horizon is smooth and well-behaved. The full causal structure of the spacetime is revealed, including the interior. The Kruskal diagram shows that the singularity is a space-like boundary at the top of the diagram, a future boundary that every time-like world line inside the black hole must eventually reach. The inside, in these coordinates, is a finite region of spacetime bounded by the horizon on one side and the singularity on the other. The Penrose diagram, a conformal diagram that compresses the infinite extent of spacetime into a finite picture, reveals the causal structure of the inside with a particular clarity. The interior is a diamond-shaped region, bounded by the horizon below and the singularity above. Every future-directed path from any point inside the horizon ends at the singularity. There is no escape, there is no alternative destination. Every possible future terminates at the same boundary. The concept of the apparent horizon, distinct from the event horizon, provides additional insight into the inside. The event horizon is defined globally. It is the boundary of the region from which light can escape to infinity. The apparent horizon is defined locally. It is the boundary of the region where the outgoing light rays are converging. During the formation of a black hole, the apparent horizon forms first and the event horizon forms later. Inside, both coincide for a static black hole but can differ for dynamic ones. The relationship between the inside and the concept of cosmic censorship illuminates the boundary conditions. Roger Penrose proposed in 1969 that singularities formed by gravitational collapse are always hidden behind event horizons. If cosmic censorship holds, the inside, including its singularity, is always sealed away. The outside universe never sees the mathematical breakdown. The inside is quarantined, its pathology hidden from the rest of reality. The strong cosmic censorship conjecture makes a stronger claim. The maximal development of generic initial data is inextendable. The inside cannot be extended through the Cauchy horizon. Determinism fails beyond it. Recent work has explored whether this conjecture holds in spacetimes with positive cosmological constant. The results are mixed. The inside of a real black hole may involve a breakdown of determinism that the classical theory cannot resolve. The proper time from the event horizon to the singularity provides a concrete measure of the size of the inside. For Sagittarius A star, roughly 20 seconds. For M87 star, possibly hours. During this time, the falling observer can make observations, conduct experiments, record data. But none of this data can ever reach the outside. The inside is a laboratory from which no results are ever published. The visual experience of the inside is computed using ray tracing in the Schwarzschild or Kerr metric. The falling observer sees the outside universe compressed into a bright disk above, with multiple images of distant stars produced by the extreme curvature. Below, darkness, the darkness of the future singularity. The visual field evolves continuously during the fall, the bright disk shrinking, the darkness expanding. The experience is cosmological in nature, equivalent to living inside a collapsing universe. The density inside the event horizon varies during the fall. Near the horizon of a supermassive black hole, the density is comparable to air or water. As the observer falls deeper, the density of the surrounding spacetime curvature increases. Near the singularity, the curvature and effective density diverge. The transition from gentle to extreme occurs over the proper time of the fall, which ranges from microseconds to hours depending on the mass. The relationship between the inside and the concept of information as a physical quantity is fundamental. Information, in the physicist's sense, is the complete specification of the quantum state. It includes positions, momenta, spins, charges, entanglement relationships, phases, everything. This information is conserved by unitary evolution. It cannot be created or destroyed. The inside of a black hole, where general relativity says information may be destroyed at the singularity, is the testing ground for this conservation law. The Landauer principle connects information to thermodynamics. Erasing one bit of information produces a minimum amount of heat. If information is destroyed inside the black hole, this thermodynamic relationship is violated. The connection between information and energy is disrupted at the inside. The no-hair theorem highlights the information gap between inside and outside. The exterior is described by three numbers: mass, charge, and spin. The inside has 10 to the power of 77 microstates. The gap between three exterior parameters and 10 to the power of 77 interior states is the information problem in miniature. Where is the information? The holographic principle says it is on the horizon, encoded in the two-dimensional boundary, not in the three-dimensional volume of the inside. The relationship between the inside and the arrow of time provides cosmological context. Black holes are maximum entropy objects. The total entropy of all black holes, roughly 10 to the power of 104, dominates the cosmic entropy budget. The thermodynamic arrow of time points toward black holes. The inside is the thermodynamic endpoint. What physics tells us about the inside is connected to the directionality of time itself. The accretion process provides context for what enters the inside. Matter spirals inward through accretion disks, heated to millions or billions of degrees. Up to roughly 40% of the rest mass energy is converted to radiation before the matter crosses the horizon. Once inside, the matter falls toward the singularity, carrying its information content with it. The inside accumulates the quantum states of everything that has ever crossed the horizon: stars, gas, dust, photons, gravitational waves. The Blandford-Znajek process, described in 1977, shows how magnetic fields can extract rotational energy from a spinning black hole through the ergosphere. The jets launched by this process extend for hundreds of thousands of light years. The inside of the black hole is the heart of this cosmic engine, the region from which the rotational energy is tapped. The inside is not passive. It is the central component of the most powerful engines in the universe. The gravitational wave signals from merging black holes encode information about the spacetime near the event horizon. The chirp signal rises in frequency as the black holes spiral inward. The merger produces the most energetic events since the earliest moments of cosmic history. The ring-down tests the no-hair theorem. Each detection confirms the exterior predictions of general relativity. None reveals the inside directly. The Hawking temperature of a black hole is inversely proportional to its mass. For a solar mass black hole, roughly 60 billionths of a Kelvin. For a black hole the size of a mountain, roughly 10 to the power of 11 Kelvin, hot enough to emit gamma rays. The smaller the black hole, the hotter. The evaporation timescales as the cube of the mass. For a solar mass black hole, roughly 10 to the power of 67 years. The inside has a finite lifetime, determined by the evaporation timescale. The Struminger-Vafa counting of 1996 provided the first microscopic accounting of the Bekenstein-Hawking entropy within string theory. For a specific class of extremal black holes, the microstate counting matches the macroscopic formula exactly. This demonstrates that the inside has genuine microscopic structure, genuine quantum states, and that the Bekenstein-Hawking entropy reflects real physics, not just a formal analogy. The four laws of black hole mechanics constrain what physics can tell us about the inside. The zeroth law says surface gravity is constant. The first law relates mass, area, angular momentum, and charge. The second law says area never decreases classically. The third law says surface gravity cannot be reduced to zero. These laws, mirroring thermodynamics, must be satisfied by any description of the inside. But what scientists discovered next was worse than anyone expected. What physics tells us about the inside of a black hole becomes increasingly disturbing as we move from the event horizon toward the center. The mathematics of general relativity describes the journey with precision, and the story it tells is one of escalating extremity, ending in a complete breakdown of the mathematical description itself. The first phase of the journey, immediately after crossing the event horizon, is deceptively calm. For a supermassive black hole, the tidal forces are negligible. The spacetime curvature is moderate. The observer would feel nothing unusual. Their instruments would function normally. They could conduct experiments, make observations, record data. They would simply be in a region of spacetime from which no signal could ever escape. But the geometry is transforming around them. The spatial dimensions perpendicular to the fall are contracting. The dimension along the fall is stretching. The observer is in a universe that is collapsing, a cosmology in miniature, contracting toward a future singularity. The mathematics of the Schwarzschild interior is closely related to the mathematics of cosmological models. The interior of a black hole is a universe in reverse, collapsing rather than expanding, heading toward a singularity rather than away from one. The visual experience of the interior has been computed numerically by several research groups. Looking outward, the falling observer sees the external universe compressed into a shrinking circle of blue-shifted light above them. The stars appear brighter, their frequencies shifted higher by the curvature. Multiple images of the same stars appear at different positions, each corresponding to photons that have taken different paths through the curved spacetime. Looking inward, the observer sees darkness, the darkness of the future singularity, a moment that has not yet arrived. The tidal forces, negligible at the horizon of a supermassive black hole, grow as the observer falls deeper. They grow slowly at first, then faster, the rate of increase itself increasing. In the final moments before the singularity, the tidal forces exceed the binding energy of atoms, then nuclei, then nucleons. Every structure at every scale is torn apart. The forces that hold matter together are overwhelmed by the differential gravitational pull across any finite-sized object. This is spaghettification, the stretching and compression of matter by extreme tidal forces. Near the singularity, the geometry of spacetime oscillates chaotically. These are the BKL dynamics, named after Vladimir Belinsky, Isaac Kalatnikov, and Evgeny Lifshitz, who first described them. Space contracts in one direction while expanding in another, then switches. The pattern of contraction and expansion changes faster and faster as the singularity is approached, the frequency of the oscillations approaching infinity. Charles Misner called this mixmaster dynamics, evoking the image of a cosmic blender churning space-time into chaos. The approach to the singularity is not a smooth convergence. It is a violent, chaotic convulsion of geometry itself. And then physics tells us something it has never told us anywhere else. The mathematics breaks. The curvature diverges to infinity. The density diverges. The tidal forces become infinite. Every physical quantity the theory can compute produces infinity. The geodesics, the mathematical paths through spacetime, terminate. The spacetime itself ceases to be defined. Physics, the mathematical description of nature, stops. This is the singularity. And it is the point where what physics tells us about the inside of a black hole becomes simultaneously the most precise and the most unreliable. Precise because the equations of general relativity, which have been confirmed to extraordinary accuracy everywhere else, produce the prediction with mathematical certainty. Unreliable because the prediction, infinite density, is physically meaningless. But here is the problem. Most physicists do not believe the singularity is real. They believe it is a signal, a mathematical artifact, a warning that the theory has been pushed beyond its domain of validity. At the singularity, the curvature reaches the Planck scale, roughly 10 to the power of negative 35 meters, where quantum gravitational effects must become important. General relativity ignores quantum mechanics. The singularity is where this ignorance becomes catastrophic. The Heisenberg uncertainty principle provides the most direct quantum argument against the singularity. At the singularity, matter is compressed into zero volume. The position is known exactly. But the uncertainty principle says infinite precision in position implies infinite uncertainty in momentum, infinite kinetic energy, and infinite pressure-resisting compression. Quantum mechanics forbids the compression to zero volume. The collapse should halt at the Planck density, roughly 5.1 times 10 to the power of 96 kilograms per cubic meter, a vast number, but critically not infinity. The inside of a rotating Kerr black hole deserves detailed attention because most astrophysical black holes rotate. The Kerr solution has two horizons, an outer event horizon and an inner Cauchy horizon. Between them, the radial direction is time-like, as in the Schwarzschild case. The observer falls toward the singularity, which is now in the future. At the inner horizon, the roles of space and time revert. Beyond the inner horizon, the singularity is a ring rather than a point. The connection between the inside and the concept of the Weil curvature hypothesis adds cosmological depth. Roger Penrose proposed that the initial cosmological singularity has low Weil curvature and low entropy, while the singularity inside a black hole has high Weil curvature and high entropy. The inside of a black hole is the thermodynamic opposite of the beginning of the universe. The arrow of time points from the low entropy beginning to the high entropy inside. The connection between the inside and the cosmological constant problem is speculative but relevant. Both problems involve the behavior of quantum fields in extreme gravitational environments. Both involve the Planck scale. Both require quantum gravity. What physics tells us about the inside may eventually illuminate the mystery of why the observed vacuum energy is so much smaller than the quantum field theoretic prediction. The relationship between the inside and the formation of the event horizon is subtle. From the perspective of a distant observer, the event horizon takes infinite time to form. The collapsing matter never quite crosses its own Schwarzschild radius. The inside, from the distant perspective, is always forming and never formed. But from the perspective of the infalling matter, the horizon forms in finite time. The matter crosses its Schwarzschild radius and continues to collapse. The inside begins. The two perspectives, consistent within general relativity, reveal the relativity of the concept of the inside itself. The non-renormalizability of general relativity is the technical barrier to describing the inside quantum mechanically. Perturbative quantization of gravity produces new divergences at each order. The mathematical framework that works for the other forces fails for gravity. The inside, where curvatures reach the Planck scale, is where this failure is most acute. A non-perturbative framework is needed. The connection between the inside and the concept of gravitational entropy provides cosmological perspective. Roger Penrose's Weil curvature hypothesis proposes that the initial cosmological singularity has low Weil curvature and low gravitational entropy, while the singularity inside a black hole has high Weil curvature and high gravitational entropy. The inside of a black hole represents the thermodynamic future, the endpoint of gravitational entropy production. The arrow of time, driven by increasing gravitational entropy, points from the smooth initial conditions of the universe toward the chaotic, high-entropy interiors of black holes. The connection between the inside and the vacuum structure of quantum fields adds quantum depth. The quantum vacuum is not empty, it is filled with zero-point fluctuations. Near the event horizon, these fluctuations are modified by extreme curvature, producing Hawking radiation. Inside, the vacuum structure is increasingly distorted. Near the singularity, the vacuum structure is unknown because the classical spacetime on which quantum field theory is defined has broken down. The inside, at extreme curvatures, is where the relationship between quantum fields and spacetime geometry becomes most mysterious. The concept of quantum complexity provides a dynamical perspective on the inside. Leonard Susskind conjectured that the interior volume of a black hole grows in proportion to the quantum computational complexity of the state. The growth is linear for an exponentially long time. The inside deepens over time, even after the exterior reaches equilibrium. The singularity is the limit of this growth, where complexity exceeds geometric capacity. What physics tells us about the inside is that it is a growing, evolving computational entity. The concept of the Planck star, proposed within loop quantum gravity, provides the most concrete physical picture of what replaces the singularity. The Planck star has the Planck density. It has a radius of roughly the Planck length. It preserves information. It eventually transitions to a white hole. The inside, at its most extreme, contains this tiny, hyperdense, information-preserving kernel. The mathematical structure of the Kerr interior is elaborate. Paths through the ring singularity lead, according to the mathematics, into entirely different spacetimes. The Kerr solution formally permits travel through the ring into regions with different physical properties, regions that can be interpreted as different universes. But this beautiful mathematical structure is almost certainly destroyed by the mass inflation instability. Werner Israel and Eric Poisson showed that even tiny amounts of infalling radiation are blue-shifted to arbitrarily high energies at the Cauchy horizon. The curvature diverges. The inner horizon is replaced by a singularity. What physics tells us about the inside of a real rotating black hole is that the Kerr interior is an idealization. The actual interior is messier, more violent, and less understood. The relationship between the inside and the concept of the Planck scale provides the natural boundary for the quantum mystery. The Planck length, roughly 10 to the power of negative 35 meters, is the scale at which quantum gravitational effects dominate. The Planck density, roughly 5.1 times 10 to the power of 96 kilograms per cubic meter, is the density at which the smooth manifold description of spacetime breaks down. The gap between the Planck scale and our experimental capabilities is roughly 17 orders of magnitude. What physics tells us about the inside near the Planck scale comes from theory alone. Every candidate for quantum gravity identifies the Planck scale as the resolution point. String theory says the singularity is resolved at the string scale, close to the Planck scale. Loop quantum gravity says the bounce occurs at the Planck density. The holographic principle says the fundamental degrees of freedom are counted in Planck units. The convergence on the Planck scale provides strong theoretical evidence for the resolution of the singularity. The fate of the Cauchy horizon has been studied extensively. In asymptotically flat spacetimes, the strong cosmic censorship conjecture holds, and the Cauchy horizon is singular. In de Sitter spacetimes, with positive cosmological constant like our universe, recent work by Cardoso, Costa, Distunis, Hintz, and Janssen has found that the conjecture may be violated. If so, the inside of a rotating black hole in our universe may contain a smooth Cauchy horizon, beyond which the future is genuinely indeterminate. The BKL oscillations near the singularity describe the approach to the end of the classical inside. The geometry oscillates chaotically, contracting in one direction while expanding in another. The oscillations become faster and more violent. The approach is not smooth but chaotic. Each spatial point approaches the singularity independently, on its own chaotic trajectory. The inside, near the singularity, is a maelstrom of geometric distortion. The visual experience of the inside has been computed by ray tracing in the Schwarzschild and Kerr metrics. The falling observer sees the external universe compressed into a shrinking bright disk above. Below, darkness. Multiple images of distant stars appear at different positions. The scene evolves continuously during the fall. The experience is cosmological, equivalent to living inside a collapsing universe. And it gets worse. The information paradox, discovered by Stephen Hawking in 1974, shows that what physics tells us about the inside is inconsistent with what physics tells us about the outside. Hawking showed that black holes emit thermal radiation due to quantum effects near the event horizon. This radiation is featureless, carrying no information about what fell in. If the black hole evaporates completely, all information is permanently lost. Unitarity, the quantum mechanical principle that information is always preserved, is violated. The Bekenstein-Hawking entropy of a solar mass black hole is roughly 10 to the power of 77. This tells us the inside has an enormous number of microscopic quantum states. The Hawking temperature is roughly 60 billionths of a Kelvin. The evaporation time is roughly 10 to the power of 67 years. These numbers define the thermodynamic properties of the inside, properties that must be consistent with whatever happens at the singularity. The firewall paradox introduced in 2012 by Ahmed Almheiri, Donald Marolf, Joseph Polchinski, and James Sully, showed that the conflict between what physics tells us about the inside and the outside extends to the event horizon itself. Three principles, unitarity, the equivalence principle, and the validity of quantum field theory, cannot all hold at the horizon of an old black hole. If unitarity holds, the smooth interior may be replaced by a firewall of Planck energy radiation. What physics tells us about the inside may be dramatically different from the classical picture. The Penrose-Hawking singularity theorems, proven in the mid-1960s, guarantee that within general relativity, the singularity is unavoidable. Roger Penrose's 1965 theorem requires only that general relativity is correct, that energy is positive, and that a trapped surface has formed. Stephen Hawking extended the methods. Together, they established that geodesic incompleteness, the technical definition of the singularity, is a generic feature of general relativistic spacetimes containing black holes. Penrose shared the Nobel Prize in 2020, but the theorems apply only within classical general relativity. They say nothing about quantum gravity. What physics tells us about the inside of a black hole depends crucially on which physics we use. Classical general relativity tells us one story. Quantum mechanics challenges that story at every turn. The resolution requires a theory of quantum gravity, a theory we do not yet possess. The Penrose process and the ergosphere provide thermodynamic context for the inside. Roger Penrose showed that energy can be extracted from a rotating black hole through the ergosphere. For a maximally spinning black hole, up to roughly 29% of the mass energy is extractable. This energy extraction changes the mass and angular momentum of the black hole, altering the inside. The inside is not static. It is connected to the exterior through thermodynamic processes that can change its properties. The four laws of black hole mechanics provide the thermodynamic framework for understanding the inside. Any description of the inside must reproduce these laws. The Hawking temperature, the Bekenstein-Hawking entropy, and the four laws form a web of constraints that any quantum gravitational description must satisfy. The connection between the inside and quantum field theory in curved spacetime provides the bridge between the classical and quantum descriptions. Quantum field theory on the Schwarzschild background describes the Hawking radiation, the vacuum fluctuations near the horizon, and the behavior of quantum fields inside the black hole. But this semi-calical description breaks down near the singularity, where the background spacetime is not well defined. The inside, at extreme curvatures, requires a fully quantum gravitational treatment. The concept of the quantum stress energy tensor inside the black hole reveals additional complexities. The expectation value of the stress energy tensor of quantum fields inside the black hole diverges at the singularity. This divergence reinforces the classical singularity rather than resolving it within the semi-classical approximation. The resolution requires going beyond the semi-classical approximation to a full theory of quantum gravity. The Bekenstein-Hawking entropy provides the most important quantitative constraint on the inside. The entropy of a solar-massed black hole is roughly 10 to the power of 77. This number constrains the microscopic structure of the inside. Any description must accommodate this vast number of microstates. The fuzzball program accommodates it through explicit counting. The holographic approach accommodates it through boundary states. Loop quantum gravity accommodates it through the quantum geometry of the horizon. The four laws of black hole mechanics, established by James Bardeen, Brandon Carter, and Stephen Hawking in the early 1970s, provide thermodynamic constraints on the inside. The zeroth law says surface gravity is constant. The first law relates mass, area, angular momentum, and charge. The second law says area never decreases classically. The third law says surface gravity cannot be reduced to zero in finite steps. These laws, which mirror the four laws of thermodynamics, constrain what the inside can look like. Any description must be consistent with these thermodynamic properties. The scrambling time, the time for the black hole to process infalling information, is on the order of milliseconds for Sagittarius A star. Patrick Hayden and John Preskill showed in 2007 that black holes saturate the quantum bound on scrambling speed set by the Margolis-Levitin theorem. What physics tells us about the inside includes this. The inside is the fastest information processor in nature, operating at the absolute physical limit of quantum mechanics. Something is wrong with our assumptions about what happens at the center of a black hole. The classical picture, with its singularity of infinite density, is almost certainly wrong. The quantum picture, with its preservation of information and its finite Planck scale resolution, is almost certainly closer to the truth. But the precise form of the quantum picture remains one of the great unsolved problems in physics. The connection between the inside and quantum entanglement provides one of the deepest threads. The smooth vacuum state at the event horizon is maintained by entanglement between modes inside and outside. The Hawking radiation arises from the separation of entangled pairs. The information paradox arises because the radiation cannot simultaneously satisfy unitarity and the smooth horizon. The firewall arises when the entanglement breaks. Entanglement is the thread that connects the inside to the outside, the classical picture to the quantum, the information paradox to the resolution. If entanglement generates spacetime, as Van Ramsdonk showed, then the inside is generated by entanglement. The inside is not a pre-existing region of space. It is a constructed region, built from quantum correlations. The inside exists because entanglement exists, and the inside breaks down at the singularity because the entanglement structure can no longer support a smooth geometric description. The connection between the inside and the concept of quantum entanglement provides one of the deepest perspectives. The smooth vacuum state at the event horizon is maintained by entanglement between modes inside and outside. The Hawking radiation arises from the separation of entangled pairs. The information paradox arises because the entanglement structure cannot simultaneously satisfy unitarity and the smooth horizon. The firewall paradox shows that, for old black holes, the entanglement must break somewhere. If entanglement generates spacetime, as Mark van Ramsdonk showed, then the inside is generated by entanglement. The inside exists because quantum correlations exist. The inside is a constructed region of spacetime, built from the entanglement structure of the quantum state. When the entanglement is disrupted, the inside falls apart. The singularity is where the entanglement structure can no longer support a smooth geometric description. The inside of a black hole, in the holographic picture, is not independently real. It is derived from the boundary. The boundary theory has no event horizon, no singularity, no classical interior. It is well-defined, unitary, and singularity-free. The inside is a holographic projection, a three-dimensional geometric image generated by two-dimensional boundary physics. When the projection breaks down at the singularity, the boundary theory continues smoothly. The error-correcting code of holographic spacetime provides the mechanism. The inside is encoded redundantly in the boundary. The code is robust away from the singularity. Near the singularity, it degrades. At the singularity, it fails. The inside ceases to have a well-defined geometric description. But the boundary information, the fundamental description, survives. The Ryu-Takayanagi formula connects entanglement on the boundary to geometry in the inside. The quantum version leads to the island formula. These formulas establish the mathematical bridge between quantum information and the geometry of the inside. The inside is built from entanglement. It is sustained by error correction. It breaks when the code fails. The gravitational path integral, summing over all geometries including replica wormholes, produces the correct unitary answer. The singularity is washed out in the quantum sum. The inside, in the full quantum theory, is singularity-free. The path integral tells us that the inside, at the quantum level, is finite and well-defined, even where the classical theory produces infinity. The ER equals EPR conjecture connects the inside to the outside through entanglement and wormholes. The inside is not isolated. It is connected to the exterior through a wormhole network generated by quantum entanglement. The inside is part of a larger quantum system, connected through the entanglement structure of the Hawking radiation. The relationship between the inside and the concept of quantum entanglement provides one of the most important perspectives. The smooth vacuum at the horizon is maintained by entanglement between inside and outside modes. The Hawking radiation arises from entanglement separation. The information paradox arises from entanglement incompatibility. The firewall arises from entanglement breaking. Entanglement is the thread connecting every layer of the problem. If entanglement generates space-time, as Van Ramsdonk showed, the inside is generated by entanglement. The inside exists because quantum correlations exist. When correlations are disrupted, the inside dissolves. The Zichat singularity is where the entanglement structure can no longer support geometry. The page curve provides the definitive test, rising entropy in the first half, falling in the second. The island formula reproduces it. Islands grow during evaporation, claiming more of the inside. By the end, the entire inside has been transferred informationally to the radiation. Black hole complementarity states that the inside looks different depending on the observer. The outside observer sees information on the horizon. The falling observer sees a smooth interior. Both are correct. Neither is complete. What physics tells us about the inside is observer dependent. The page curve, the specific pattern of entropy that characterizes unitary evaporation, constrains what happens to the information inside. The entropy rises during the first half of evaporation and falls during the second half. The island formula reproduces this curve. Quantum extremal islands, regions of the inside that belong informationally to the radiation, grow during evaporation. By the end, the entire inside has been claimed by the islands. The information is transferred from inside to outside. The Hayden-Preskill protocol shows that individual quantum bits can be recovered from the Hawking radiation after one scrambling time, milliseconds for Sagittarius A star. The inside is not a permanent prison for information. It processes information at the maximum quantum rate and returns it eventually through the Hawking radiation. The connection between the inside and quantum computation provides a dynamical perspective. Susskind proposed that the interior volume grows because quantum complexity increases. The inside is not static, it deepens over time. The singularity is where complexity exceeds geometric capacity. The inside is a growing space, generated by computation. The concept of the stretched horizon provides a physical picture of the quantum degrees of freedom at the boundary of the inside. The stretched horizon, one Planck length outside the mathematical event horizon, has temperature, entropy, and viscosity. It is the physical realization of the quantum states that encode the Bekenstein-Hawking entropy. The page curve provides the definitive diagnostic for whether information escapes the inside. Don Page showed in 1993 that if evolution is unitary, the entropy of the Hawking radiation must rise during the first half of evaporation and fall during the second half. The island formula reproduced this curve in 2019 and 2020. Information is preserved. What physics tells us about the inside includes this. The information that enters the inside is not permanently trapped. It is processed, scrambled, and eventually returned through the Hawking radiation. The Hayden-Preskill protocol shows how quickly individual bits can be recovered. If a quantum bit is thrown into an old black hole, it can be recovered from the subsequent radiation after one scrambling time. For Sagittarius A star, this is milliseconds. The inside processes information at the maximum rate permitted by quantum mechanics, then returns it. The inside is not a vault. It is a processor. The Penrose process and the ergosphere of rotating black holes add thermodynamic context. Energy can be extracted from the ergosphere. For a maximally spinning black hole, up to roughly 29% of the mass energy is extractable. The inside of a rotating black hole is connected to this energy extraction through the thermodynamic laws. Any description of the inside must be consistent with the extraction dynamics. The Weyl curvature hypothesis proposed by Penrose connects the inside to the arrow of time. The initial cosmological singularity has low Weyl curvature and low entropy. The singularity inside a black hole has high Weyl curvature and high entropy. What physics tells us about the inside includes a thermodynamic asymmetry. The inside has the highest entropy, the highest Weyl curvature, and the most advanced position along the arrow of time. The connection between the inside and the cosmological constant problem is speculative but intriguing. Both involve the behavior of quantum fields in extreme gravitational environments. Both involve the Planck scale. Both require quantum gravity for resolution. What physics tells us about the inside may eventually illuminate the mystery of the vacuum energy. The relationship between the inside and the formation of the event horizon is subtle. From the perspective of a distant observer, the event horizon takes infinite time to form. The collapsing matter never quite crosses its own Schwarzschild radius. The inside, from the distant perspective, is always forming and never formed. But from the perspective of the infalling matter, the horizon forms in finite time. The matter crosses its Schwarzschild radius and continues to collapse. The inside begins. The two perspectives, consistent within general relativity, reveal the relativity of the concept of the inside itself. The non-renormalizability of general relativity is the technical barrier to describing the inside quantum mechanically. When physicists try to quantize gravity perturbatively, each order introduces new divergences. The mathematical framework that works for the other forces fails for gravity. The inside, where the curvature reaches the Planck scale, is where this failure is most acute. What physics tells us about the inside is limited by this mathematical barrier. The concept of the stretched horizon, developed by Susskind and collaborators, provides a physical picture. The stretched horizon is a membrane 1 Planck length outside the event horizon. It has temperature, entropy, viscosity, and conductivity. It processes information. It is the physical realization of the quantum degrees of freedom of the inside. What physics tells us about the inside is encoded on the stretched horizon.